Hi Shivani.
Hi, Aesha. How are you?
I'm good. How are you?
I'm good. I see you are in a very exotic location. I'm in Netherlands at the moment. So I'm doing my research here. So I was in Australia for the past 7 years, as you might also know. And then recently for my another postdoc position, I moved to the Netherlands. Now I'm working with the Astron, which is the Netherlands Institute for Radio Astronomy.
Oh, okay.
We met at a pub in Sydney. So there was this event called Science in the Pub where
I was giving a
Ah,
talk in a pub, so that was a very
yeah,
chilled out environment, and we were talking about science and cosmos and universe. It was just awesome. And then I met you and
yeah.
you asked question and we just clicked.
let us hear a little about your research because your research is really fancy.
Fast radio bursts, these are flashes of radio waves that are coming from distant galaxy halfway across the universe, and they last just for a couple of millisecond or microsecond. The
Hmm.
coolest thing about these bursts is that they tell us a lot about our universe, because when they originate in their own galaxy, they travel through the space between the galaxies when they reach us. So they carry all that information about how the intergalactic gas looks like. So they are the direct and very powerful probes of studying the structure of the
Hmm.
universe. So the most fascinating thing about the FRBs is their mysterious origins. We don't know what produces these type of signals, but I can guarantee say that they are not aliens. There are some astrophysical sources up there in the universe that produces this signal. So for very long, we used to think that there is only one type of FRB, which just flash gives a radio flash, produce a radio flash, and then it's gone. And then you follow up that patch of the sky for years and years, and you don't see the signal again. But in the recent times, it has been found that there are indeed few FRB sources that do produce repeating signals. So it's
Hmm.
not periodic, it's very random. It can happen anytime, so you don't know when it's going to happen. And
Hmm.
but if you keep staring at that patch of the sky for long enough, eventually you'll see another burst from the same patch of the sky with the similar properties of an FRB. So then there's sort of two classes maybe. So one non-repeating FRB could be, some sort of catastrophic events like colliding black holes or colliding stars, or any such collision between two compact objects in which the source essentially destroyed itself, and that's why it never seen again. But then on the other hand, it could be a source which is not destroying itself. Like for example, if you look at our sun, it emits these CME or solar bursts, right? So in a similar case, there might be some powerful magnetars out there in the universe. For example, magnetars are highly magnetized neutron stars. So there is a theory that these neutron stars can actually produce such bursts by emitting giant flares. In that case, the source does not destroy itself, and then it's one of the theories of, the for the FRBs that do repeat. So we are still not sure what is the actual cause, but there is a lot of theories around it. And the most exciting thing happened was like few years ago, we found an FRB like signal coming from our own galaxy. So
Oh,
that was pretty cool, because everything is so far away in the universe and you can't just really go there and see. But with
hmm.
things happening in our own galaxy, we saw that it was coming from a direction of this highly magnetized neutron star, which is a magnetar. So then, okay, and we did see it repeat. So then sort of, give us an idea of, okay, so maybe not all FRBs, but some of those FRBs are created by these highly magnetized neutron stars. And then some of them are still a mystery, which could indeed be a more massive neutron stars, or could be completely different thing that we haven't anticipated just yet. So it's still very mysterious, and that's the fascinating thing I find about FRBs, and that's what keep me going, and wake up in the morning and let's study and try to see. And yeah, that's why I find this field very fascinating.
It is really fascinating. I have a couple of questions there. So, what is a neutron star? One. And another thing, like if we are walking down the street, like with our naked eye, can we see such a burst in the sky?
So, first, I will answer your question about neutron stars. So, every star, when it becomes a certain size, if you see a normal star, there's a constant tug and war happening between the gravitational forces and the radiation pressure from inside the star, which is keeping it stable. But at some point, the gravity takes over and the stars start to collapse and it goes supernova. It goes into an explosion. And depending upon the initial mass of the star, it can actually explode and become, so the remnant can either be a neutron star or a black hole. So neutron star is like the nucleus, it's full of neutrons and it's so dense, like it's only like one solar mass or approximately the mass of the sun, but it's so dense, it's a very dense, and it can fit inside, the size of Sydney, for example, but it will
Oh,
weigh more than the mass of the sun itself. So it's
oh
like
my.
super dense, super hot stars called neutron stars. And then those are one of those. And then when these neutron stars becomes magnetized and have very powerful magnetic fields, then it's just a monstrous source, and it can do various sort of things, which and maybe produce FRBs as one of its things that it does. The next question you asked was about, okay,
Can we
the
watch them? Uh,
so these are radio flashes, so which means that they are emitted at radio frequencies. So if our eyes can see radio frequencies, then yes, definitely you see these fast radio bursts happening all over the sky. But our eyes only see the optical spectrum of the wavelength. So we can only see, red to violet colors, and we are limited in that sense. So we cannot observe FRBs if you look at the sky. So yeah, because
but
they're only.
maybe some other species, like maybe dogs or somebody who can see radio waves.
Exactly. Yeah.
Yeah.
So, for example, I know bee can see in ultraviolet light. So, I don't know if there are any animals who can see in radio light.
Radio.
Then yeah,
Yeah.
definitely. Yeah. You need radio eyes to see these FRBs. But if you have a radio eyes, then it will be, fireworks everywhere all the time on the sky.
Yeah, as they say, like as your sight, so is your world. So world is different for different species here. Okay,
Yeah.
that's
Yeah.
interesting. And would you like to show us some pictures or anything?
Oh yeah, so
Uh,
I will show you a very cool animation that we did when I was at CSRO. So this was the very first localization, like with using the telescope called ASCAP, which stands for Australian Square Kilometer Array Pathfinder. We were able to localize. With localization, I mean we were able to pinpoint the exact galaxy of the FRB for the first time, because as I said, most of the FRBs are only happening once. So catching them just in time and then tracing it back in journey and placing it to its home galaxy is a very crucial and very difficult task, which luckily with the most updated instruments and technology we were able to achieve when I was at CSRO. So that's the animation which will tell you about that. So I will play that now. Share. So
yeah.
you see the fast radio burst, and this is how the burst looks like. So the another important property of the burst is this sweep, which is a very beautiful property called dispersion. So dispersion is, you will see it in the video next when I will play. Okay, it has some audio as well. So I will just shut up when this video is being played. So here the colors represent different radio frequencies. So the purple one is a higher frequency and the red one is a lower frequency. And when the signal passes through the stuff in the line of sight, like for example, it passes through this galaxy, then the low frequency electrons, they get delayed. As you see, the red is getting further and further, and then it passes through another galaxy along its line of sight. So the higher frequency don't interact with the medium, but the low frequency does, and that's why it gets delayed. And this is the telescope ASCAP, and you see these various radio frequencies. Our telescopes are capturing it, and then they are being processed in our supercomputers. And now you will see that dispersive sweep because the low frequency electrons have delayed in their arrival. And then you can see because FRB is passing through all these galaxies, it encoded the information about all the stuff that it's been gone through. And that's all information is available in that dispersion sweep that you have seen.
That was amazing. That was really good. What kind of information do FRBs give us about the galaxies that they pass through?
So this is how a typical burst looks like. So you see in this case, you have a sharp peak, but then you have this exponential tail. So this tail is because of this burst has undergone scattering, which tells us there are some inhomogeneities along the line of sight that burst has gone through, which has caused this scattering. And then these are the different type of bursts that we have seen. For example, this is pretty broadband. So this is time here in x-axis, and this is frequency. So this burst shines over a bandwidth of 400 megahertz. And then you see some of the bursts are, they do not have a scattering tail. So we call this exponential thing as a scattering tail. So some of these bursts are narrow, they do not have a scattering tail, and then they are very, sub band. They do not shine across the whole band of the telescope. And then this is narrow band. And then you see some of them are complex, like this one has this two peaks, and then again a different dynamic spectra here. And this one is just, a bunch of multiple peaks, and you see the spectrum is also a bit different than this. So these are the different type of bursts which are telling us different things about, their line of sight journeys, and we just have to encode them by studying their polarization properties, their dispersion measures, and their scattering properties.
Okay.
It's just like you see a star, right? You see a star, and it has taken ages to get the light of the star to reach to us now, like depending upon how far the star is. So this is something similar in radio. So it's just a signal that people are seeing, or we are seeing from far away. But yeah, with this signal, as you can study the stuff between the galaxies, then eventually when you have lots and lots of FRBs, like thousands of FRBs in every direction, then there is a way that in which you can, start learning about dark energy and dark matter. In that case,
Oh,
eventually when you understand what dark matter is, then yeah, then maybe you can send one astronaut from one galaxy to another galaxy in a wormhole or something. But that's very science fiction at the moment.
like we have always seen that we need medium to pass through. The
Hmm.
physical things have need medium. So between the galaxies, is there anything which helps these radio signals pass through them, or there's like it's empty?
So again, it's so we have a galaxy, and then there is this intergalactic medium, which is the stuff between the galaxy, which people think is a warm hot intergalactic medium. Is like, some
Okay.
sort of warm hot, it's called IgM, intergalactic medium, warm hot plasma. So
Okay.
that's between the galaxies. So with the properties that we have seen for FRBs, what we have found so far is that that is indeed how what people think of the stuff between the galaxies. It's not, very clumpy or anything. It's very low density, less magnetized plasma which exists between the galaxies, which what we have seen directly from studying FRBs. But yeah, it again depends upon different line of sight, or what line of sight an FRB is passing through. For example, if an FRB is indeed passing through, just the center of the galaxy, then it will encounter a lot more electrons along its line of sight, because there's, so much messy things happening around the center of the galaxy with the black hole and everything. So then it will have more contribution from that surrounding, so that will affect the dispersion measure and the properties that we will measure for FRBs. That's why we cannot study the universe with just one burst. We need thousands and thousands of bursts coming from all the directions to map that structure of the universe.
Okay. And like knowing about universe and knowing about these spaces between the galaxies, does it help us understand how the universe might have originated and how it's progressing?
So again, it all comes down to, dark energy, because that's will define the fate of our universe, and we don't understand about. So like out of 100% constitutes of the universe, we hardly understand only 5% of it, and then the rest is in the form of dark energy and dark matter, which we do not understand. So potentially, yes, first FRB will help us in understanding the whole 5% of the matter, so out of these 5% baryonic mass, like which the normal matter that you and I are made up of, we know 50% of us of that matter is in the form of, human beings, galaxies, but the rest 50% of it is still missing. So like 50% of the 5% that we know, we have no idea what it is, and
So
that is something.
we have
Yeah.
no idea about ourselves as well. Like we have dark matter inside us as well.
So we are made up of total baryonic matter, like atoms, electrons. We are made up of baryonic matter, and then the 5% constitute with the matter that everyone is made up of, and the universe is made up of. That's only 5%, but even 50% of that 5%, we haven't measured it directly. We know, so that is the type of matter which is the missing baryon. So it's we know it's baryon, it's not dark. We haven't even touched the dark things. So dark matter and dark energy for FRBs is just an unexplored territory at the moment. We are only talking about that 5%, and 50% or 60% of that 5% we know is normal matter. But then again, that little left bit is now we are thinking, okay, so that sort of matter which lives in between the galaxies, because that's what FRBs are probing. So now we are getting more confident, and that is indeed, warm, hot, intergalactic plasma that exists between the galaxies, that could explain that remaining 40%, 50% of baryonic matter that we are so confident we know, right? and
Oh
and
my god.
maybe in the future, when you have, thousands and thousands of FRBs, you will start to understand maybe dark energy. And then once you understand a dark energy, then you will know, okay, how our universe is going to evolve, because it's the dark energy which is accelerating the universe at the first place. So once you know
Okay.
about this dark energy, then you can say something about the fate of the universe. But again, this is like way far, into the future. So first we need to understand better the things that we already know. And FRBs is an independent way to check if the things we know about, our baryonic matter is indeed correct or not. And it's showing that our understanding has been okay so far. So it's not like we are completely wrong. So FRBs and studies and independent studies of FRB do agree with what people have seen using like quasars and other cosmological tools. Yeah.
Okay. How did you get interested into this kind of world of knowing about the universe, and what was your drive as a kid?
Yeah, so as a kid, I was, always watching Carl Sagan's shows and Brian Greene, and looking at, this beautiful Hubble telescope pictures, and that whole like the whole show and the pictures that I saw were just so amazing. And I think because of that, I just got interested into science. And then I used to know, because we lived in India and everything, and then we just go at the roof and, just look at the stars. And then I'll ask my parents these silly questions, because I knew that sun is made up of hot gas. Then I will ask, okay, is the moon, is it like also a hot gas or no? And then I learned about moon, that it's a rock. And then I used to visualize, okay, so all these little shiny things are rocks, but that's not true. So I was very curious about the world around us, and I knew from the beginning that I want to do astronomy. But during that stage in India, with no internet and no resources, it was really hard to actually, what is the correct rule to follow. So I ended up
Which
doing
which part of India were you in?
New Delhi. So I was born and brought up in New Delhi. So yeah, even in New Delhi, so like I know the now I know, like after a few years after doing sort of research, that there are these facilities in Pune. But at that time, when I was, in my 10th standard and 11th standard, without any internet those days, it was not just, I did not know about any such things. So, but I wanted to know that I want to go in this line, but there was no guidance, nothing. So I just ended up doing what, most people do after their 12th, go for these, entrance exams, this horrible entrance exams, and then, ended up into an engineering institute because that's what everyone was doing. And
Hmm.
then I graduated as engineer after 4 years. And then when I got employed in a company, then I was like, no, I don't want to do this. And then I
Uh, one
started
thing, one thing. Why did you find these entrance exams horrible?
entrance exam. They're so stressful. So first
Uh,
first of all, I first of all, I'm the type of person who, if you give one question, I want to take my time to solve it because I want to think about it. So, and the fact that the clock is ticking and you have to answer, these 100 questions in that, so that is just too stressful. Instead of actually thinking about the question itself, I will think, oh my God, 90 minutes remaining, oh my God, 60
yeah,
minutes remaining. So
yeah,
that sort of environment just didn't work for me. And that's why, even though I knew the subject, I knew what I'm doing, I just could not solve the problem in that given time,
yeah. And like
confined.
when you have built such a long career in STEM, do you feel like that kind of effort was required at that time? Like in high school, was it necessary to know a lot and solve it really quickly? Like, does it work like that in real world?
No, I think that, so I don't remember half of the things that I was taught in high school, right? For which we were cramming and giving exams and passing all these things. So I think, like, what should be the ways to do things in a very practical way. Like if you are studying a topic, you should do it in a very practical way, work on it, maybe do a short project so that you actually get the understanding of it, not just for the sake of, getting an exam done. You should be really able to understand it, and once you understand it, then you enjoy it, then you don't feel, a pressure about an exam, because you know that you really enjoy doing that. So I think all that exams and 10th exams and 12th exams, I don't remember half of the things that I was taught, and I only remember the things that I'm currently working on and which are slightly related to my work. And that's great because I'm doing it every day, and that's what's important. So I think the practical knowledge is very important for, from the very beginning. After my engineering, after my job, then we had like a nice internet connection at home, the cyber cafes, and I was old enough to, start making my own decisions. And then I thought, okay, this is not what I want to do. I want to, go abroad. And because I have done in engineering in physics and not, sorry, engineering in electronics and communication, I obviously did not have a very great understanding of, concepts of physics and all that. And that's why wherever I apply in India, you have to again go through these nest and jest and all these sort of exams, which are again were not for me. So I did sat on few, I got like negative marks. I was like, okay, I just cannot do, astrophysics and science in India. It's not just for me. And that's how I ended up going to Raman Research Institute for a visiting student program. And that's how I learned about radio astronomy, doing working on a project there with Professor Dwarkanath. And then I developed a basic understanding of, okay, this is how the research life is, this is what radio astronomy is, this is how you look at the sky at different frequencies. And then there was no turning back. And it was like, and then I talk about networking. Yes, networking did play a very crucial role, because I remember there was this meeting happening at RRI when I was there, and people from Australia, people from US, and everyone was there talking about one telescope and its future plans and discussing science. And then in that conference, I made sure, that I approach each and every professor and ask for PhD student and ask for PhD opportunities. I had a list of all these professors that I want to talk to. I did a brief, internet lookup to see what are their interests, and then I'll just go and talk to them and see if you have any PhD positions I'll be really interested in. And that's how I ended up with one of the professors who actually invited me for a summer student program in Perth. And then I went to Perth, and then after that I applied for few PhD positions in Australia, and that's how I got one. And from that, like, the the decision of quitting the job and going to the RRI for a hands-on experience about radio astronomy was a very turning point in my life, and it just, slingshot me to this position where I am at the moment. So yeah, I'm very grateful for opportunities like visiting student programs and summer programs.
Yeah, like whenever you start a long-term commitment with somebody or with any subject, it's very important to do some hands-on experiments in those field or some kind of training or some kind of 3 month project kind of a thing to just know the system. So sometimes it becomes difficult, like with the mindset of completing things year by year and starting very quickly, but it really helps you, and it makes your mind up for that area of work. So I think this kind of the internship that helped you in Perth was really a good uh, decision by you.
Hmm.
And I also feel like, especially at this time when government of India is promoting research and STEM fields, that this environment of opening the doors and not making research very, if you if you get passed through these kind of tests, then only you are able to do the research. It's not how things work in the other parts of the world. So if you want to do research, you meet a professor, you talk to them, and it's
Yeah.
just the matter
Yeah.
of getting,
And
yeah,
and and for me, I did not. So I told you, right? I did my engineering for 4 years, in which we had only physics one and physics two, very basic for the first year, and then I did not do any coursework in astrophysics because I wanted to learn. I did few of these online courses in Coursera just for my own knowledge, and then I still remember when I was sitting with my professor from my very first day of research, and he asked me, "Do you know pulsars and Jocelyn Bell?" And I was like, "No, I don't know. What are you talking about?" And then he was like looking at me like so shocked, and I was like, "I just don't know. I'm so new." So even when I started my PhD, I had no clue what a pulsar is. And I learned
yeah,
along the way, and then I gained all that information. So I would say that the learning curve was very steep when I was in PhD, but that sort of information is not needed. Like, for if I can do a
yeah,
PhD and become a scientist, I think all of us can be, if there is that curiosity and if there is if that passion, because our field is just passion driven. There is no motivation other than, passion for
yeah.
curiosity. So yeah,
That
I
is
would
one thing that you decided to take this steep learning curve. That was a great job on your end as well. But the thing is, the system didn't restrict you from entering without prior knowledge. So these are the things which you can learn on the way. You don't need to know them beforehand,
yeah.
right?
Exactly. So the qualification or the criteria that my university saw is just, okay, you have these many marks. Okay, this is good enough, and then you give your IELTS exam. You show that you are proficient in English, and then my research with RRI and NCRA that I did and win the Perth, that was, just the turning point, because they knew I have been working closely with these people, and the references that you make along the way, that was the major thing, like your experience and your references, and that's what you get when you network with people. So yeah, definitely networking played a very crucial role in my career. Yeah.
That's amazing. Your story is very unique, and I think it will be really helpful for a lot of students. Would you like to share anything else?
I would just say, you don't have to be super genius. Like, for example, if I say something, I'm an astrophysics, especially in India, they will say, "Oh, you must be very genius," right? I'm not genius. I'm a hard worker, and I'm very curious, and I want to learn things, and I want to do it in a smart way. And it's just a curiosity-driven science. And if you are curious, then astrophysics is for you. You don't need to be like a genius, like Albert Einstein, to be in this field. And nowadays, astronomy and this whole astrophysics is so collaborative that if you don't understand the actual theory, like, for example, I'm an observational person. I observe using the telescope, and then I analyze the data. So more of a data driven astronomy than actually writing down equations and like Einstein creating different theories. I don't do that sort of work. But nowadays, astronomy is such a collaborative field. Like, even even if you don't have those skills, you can collaborate with some theorists. So you can observe, like what I do in my research at this particular moment. Like I ask time and I observe with telescopes, because I know how telescopes operate. I look at the data. For that, you can develop all these skills while you are in your PhD. So I look at the data and then I try to interpret the results. And from theory wise, I will get in touch with some of the theorists. I will pass on my observational features about an FRB or whatever to them, and then they will make models and they will come up with some theory, and then we will collaborate, and then we'll just publish a paper together that will talk about everything about that source. So because of this collaborative of nature of the research, you just not have to have everything for you. You always can collaborate with different people who are experts in their field, so you don't have to become like have a stress of being expert at everything. You just know how to get your data and look and what understand what FRBs are. And I think if you are an expert of that, you're curious enough, your job is done. Else can be done in a very collaborative way as well.
Uh, so that reminds me a thing. When I was applying for PhD, Professor Raghavan Rangarajan, he was mentoring me and he was suggesting, how to go about applying for
Mm.
different PhD topics and stuff. So these friends of mine from the same institute suggested me that, you don't know these softwares, you don't know these conceptual topics and stuff. So the guy said, if I were you, I would just take a break for a year. I would learn all the topics and then I would think of applying for PhD. So I thought that, yeah, that makes sense. I don't know a lot of foundational stuff and I should take a break. And a couple of days later, I met Raghu sir, and he said that don't take advice from the people who have not gone on that journey. So they are doing their PhD elsewhere, you are planning elsewhere, and this is not how it works. So if you want to apply, you just apply and you go
Yeah,
ahead with it. You don't need
yeah,
to know a lot of things. So exactly as you said, there are few softwares that you might not need know of, and you will collaborate with others. So
yeah.
currently, how many people are you collaborating with?
So during my PhD, I had more than 100 people on my first author paper, like more than 100
Oh,
people,
oh
because
my
I was
God.
doing because I was doing multi-wavelength follow-up of FRBs. I only know to find FRBs at radio frequencies, and but then because we didn't know maybe FRBs have multi-wavelength counterparts, they also shine at different lights. So then we collaborated with optical astronomers, X-ray astronomers, people from Antares collaboration to look for neutrinos, and different facilities like in the US, in Europe, everywhere. And then and yeah, and then we concluded that FRBs do not appear at any other frequencies other than the radio frequencies. So in my very first paper, even though I'm a radio and astronomer, I collaborated with optical people. I don't know any of the analysis of the optical, once the data gets done from the optical facility. I don't know any softwares about that. And for that, I collaborate with people. And similarly, for high energies, I don't know how to do the reduction of the data. You can always learn. But as a PhD student, and an overseas PhD student, I had only 3.5 years. And
Yeah.
then I have these visa constraints and this scholarship ending
Hmm.
constraints. So in principle, I could have learned all that, but if it had taken a lot more
Yeah.
time, and because I was in that 3.5 years of constraint, I thought it will be better if I focus on what I am expert at, the radio things, and let the other people do other wavelengths. And then we all put our results together. And then I was able to publish my paper after like 1 year of whole this collaboration and talking to different people. And then you also find some people are more responsive, some people are not, and then you have to take everything into account. So that was
Yeah.
my
Yeah. And that's how it works in real world. There is limited time of your life. You cannot know everything. So yeah, this is the skill that you need to learn during your schooling, which is collaborative skills.
yeah,
So
yeah.
yeah, that makes sense.
Yeah,
Uh,
so
I,
after writing that first paper, I should say that my personality has changed by 180 degrees. Like I used to be a shy person, not talking to
yeah.
everyone. And now I'm just like, when I want to be, I am a very extrovert person and go and talk and introduce
Yeah,
myself, won't feel shy. So that part of the collaboration actually also changed my personality. So that is another skill if you want to be in such a field, is that you should be able to talk to people. You should be able
yeah.
to go and introduce yourself to them. So that is another important skills, like for you to be open about what you are doing and not, a shy or an introvert person. I am an introvert person, but for this thing I become, extrovert, because this is how it works. This is how you collaborate and make connections with people. Yeah.
How did you find this um, connection? I mean, you have been in Australia after India, and now you
Hmm.
are working in Netherlands. So how did
Hmm.
that work out?
Yeah, so when I completed my PhD, I there was this very nice job opening with Keith Bannister at CSRO, who suddenly, came very much interested in become very much interested in localization of FRBs, and I have just finished my PhD on FRBs, so I applied for that position. So in that way, I was able to stay for another 3.5 years at Australia, working at different telescopes. And after that 7 years, I wanted to, explore a bit more, because I think for research it's good if you change continents, because then you get to know different people, how they think, you get to understand, have a better understanding of different telescopes. And now I'm working with this European VLBI network and LOFAR, so which is a totally different type of telescopes that I have worked in when I was in Australia. So that's what. And the group that I'm working with, Jason Hessels, he really knows what he's doing in this field, because he's one of the experts as well, and a very nice person. So I thought this might be a good. And plus I wanted to travel Europe. That was, I'll be honest, I wanted to travel Europe, and I was like, this is the best thing, like for 3 years, right? So every postdoc position is a contractual position, so 3 years here, 3 years there. So I ended up applying at Jason's job. I applied everywhere, like I also applied in the US and everywhere. um, and then Jason asked for an interview, and I got selected for this position. And while I was here, I then applied for one of these grants, because again, another important research skill that one should have is to be able to ask for money for their own funding, and for, building instruments. If you want to start your own group, you should be able to convince the politician that this is very important, and for them to give you money to actually do it. So then I
Hmm.
applied for one of these grants from the NVO, which is the Dutch Research Council. And then I was awarded a Veni grant for 3 years to do my own research. So
Oh,
I basically applied for my own, salary and all the funds that I am currently using. So that was another,
wow.
like, a step further in the career. Like, this is also very important, if you, especially if you are applying for permanent jobs, to be able to convince people that you are, you have that skill to acquire external funding as well from government, to do your own research or to build your own instruments. So that is another skill. Yeah. So
That's amazing.
that's how I got involved in the Netherlands, and I'm having a blast here, and, learning about different telescopes, and how Europeans think as compared to how Australians think. Because if you traverse through different group, oh no, I know Keith will think like that, but now I know, okay, Jason will think like that. So you so it's the whole development of, interacting with different groups and what they think. And yeah, it's been great so far, other than the weather is so bad and it just makes me feel low. But when it's
Hmm.
a nice sunny day, I'm a very happy girl.
So when you were doing your PhD or whenever you publish, do you look at that, this publication is really popular amongst Australians or Europeans, or so that it gets you recognition everywhere, so that your chances of getting job after PhD increase? Like, what do you take into account to just make sure that you are connected with the right people by the end of your PhD?
Yeah, so initially when I was doing my PhD, so I think the aim was to just go for the free journals which has good impact factor. So MNRS is definitely one of the good ones which has good impact factor and is also free. And when you get some funding, like for example, when my professors were able to give me some money for, publishing, then I decided to target the American audiences, because, and then I started publishing in the astrophysical journal, the ABJ letters. And there's a reason for that, because when FRBs were a very new field, there were a lot of people from America who was, putting out different papers about different conclusions. And then in Australia, we were able to localize the very first FRB that changed a bit. So that changed their conclusions a bit. So I wanted to make sure that this result is out there in the American audience, because they have always thought that FRBs, are live-in dwarf galaxies. They are formed by something progenitor like superluminous supernova. And what I found was different. So I wanted to make sure that that message is received to that audience, and that's why I ended up publishing, even though the publishing cost was like, 2,000 euros or $2,000 Australian dollars, a lot. But and at that point, I wanted to specifically target American audience. And now in Europe, with Astron, publishing in the ANA, which is the European journal, is pretty much free. So I'll aim for that, unless I want some very hot result to be published quickly. For then I will go for ABJ letters, because they are very, so all the letters and notes, they are very speedy in their publications. So if you want to have a very hot result out very soon, then you go for those. But I've never published in all these nature and astronomy, nature and science as a first author, because again, these are, meant for very hot results, which has never been detected first, and you are doing it for the first time in publishing. So all sorts of journal are mostly meant for that. So some of our results were, yes, published in nature and science, but I haven't been a first author for those ones. Yeah, and those mostly, like, attracting people, like, we have found this for the first time, okay, so then that's a nature paper. But if you really want to talk like scientific details about it, then it makes sense to put it in one of these astronomical journals, like, MNRS or APJ.
Okay, thank you so much, Shivani, for your valuable time. I think you have covered a lot of areas for students to ponder upon and take right decisions for their career. So
Yeah,
thank you so much.
and thanks to you for having a platform at the first place, so that, I can share my views, and that can help students in the future. So thanks to you, Asha, as well.